Hello everyone, so this is for GCSE Science Trilogy, Foundation Tier Chemistry paper, paper 1, that pupils sat in May 2018. I'm going to walk through this paper and outline how I would have tackled it. Now, as with all of my videos, the link to the exam paper and the mark scheme is in the description, and also for each question there is a link to a specific revision video if you struggle with the content for one particular question and you need to go back and revise it. So, starting with question number 1 then. This question is about structures and bonding. It shows part of a structure of a calcium oxide, which is CaO. And you've got the diagram here. So you see it's got negative charges and it's got positive charges. What type of bonding is present in calcium oxide? So obviously you'll have the periodic table in front of you and you can identify that calcium is on the left side of the periodic table. So it is a metal, and oxygen is on the right hand side of the periodic table, therefore it's a non-metal. So you have a metal and a non-metal reacted together, and that always produces an ionic substance. So the answer is ionic. For covalent, that is what you would get if you had two non-metals. Ionic, as we've said, is a metal and a non-metal, and metallic is when it is just a pure metal. Macromolecular means a large amount of molecules all together, so it's not that. Question 1.2. Figure 2 shows part of a methane molecule, which is CH4, and you've got the diagram of it here. What type of particle is present in figure 2? So, an ion is what we just saw before on figure 1, when it was charged. There are no charges in this, so it's not an ion. A lattice is when you have loads of ions all together. So there's only a small amount of atoms here, so it's not that. A molecule is when you've got non-metals that are covalently bonded together, and this is what we've got here. Carbon and hydrogen are both non-metals, so therefore it is covalent bonding, and therefore it is a molecule. We can tell it's not a polymer because a polymer would have loads and loads of repeating units. It would be a really long chain of atoms. Figure 3 shows the structure of C60. Okay, complete the sentence. And you've got these 4 words here. The structure of C60 is one of these 4 words. If we go through them, diatomic means you would have 2 atoms. Okay, tri meaning 3, di meaning 2. There's more than 2 atoms here, so it's not diatomic. Giant ionic would again have ions in it, which are positively or negatively charged. That's not in this diagram, so it can't be that. And it's not a metal, so therefore we are left with a fullerene. So the structure of C60 is a fullerene. A fullerene is when you've got carbon atoms arranged in a tube or a sphere. Okay? So, figure 4 shows the structure of graphite. What type of bond is labelled A in figure 4? So you've got the bond here between 2 different atoms, and it's represented with a dashed line. Now, 99% of times, a dashed line is represented by a covalent bond. You should also know this because in graphite, carbon is bonded to carbon. Okay, these are both non-metals, so therefore when you've got 2 non-metals bonding together, it makes a covalent substance. In question 1.5, it says, in graphite, each carbon atom forms bonds with other carbon atoms as shown in figure 4. How many electrons does one carbon atom use to form one bond? Okay, so if we look at these carbon atoms, they join to 3 other carbon atoms, the ones that are in the middle. Now, in order to do this, what they do is share 1 electron with each other to get a full outer shell. Their 1 spare electron, what they do is allow it to become a delocalized electron, which moves between the layers of graphite, and therefore it can conduct electricity if a voltage is applied. So your answer is 1. An electric current is passed through copper. Figure 5 shows the apparatus used. So you've got a power supply, you've got a bulb, you've got 2 electrodes, and they are joined by a piece of copper. Complete the answer from the box below. So you've got gas, liquid, solid, and solution. Figure 5 shows that copper conducts electricity as one of those words. And we can see from the diagram, you've got a solid piece of metal between the electrodes, so therefore the answer is just solid. Question 1.7, complete the sentence. Copper conducts electricity because of the movement of delocalized something. So it's atoms, electrons, ions, or molecules. Now, copper is a metal, and in the structure of the metal, you have the atoms, and all of these atoms give up an electron or 2, and these become 3 delocalized electrons. And when a voltage is applied, they can move through the structure and carry the heat or electricity. So the whole reason that it can conduct is because of the movement of delocalized electrons. That is what makes metals really, really good conductors. Question 1.8. Figure 6 shows the apparatus used to investigate the effect of electricity on sodium chloride solution. You've got figure 6 here, you've got your power supply, your bulb, and your sodium chloride, but this time it's in a solution. Complete the sentence. Figure 6 shows that sodium chloride conducts electricity when it's either dissolved, gaseous, or molten. So we're just specifically looking at what is in figure 6, and we can see that our sodium chloride, well, it's definitely not in a gas form, and if it was molten, it would not be in a solution. It would be just by itself. If it is a solution, it means it is dissolved in. Okay, so in this situation, our sodium chloride, our salt, has been dissolved in water, and because it's been dissolved, it can conduct electricity. Question 1.9. Sodium chloride is made up of ions, so we know it's an ionic bond. Figure 7 shows the apparatus used to investigate the effect of electricity on solid sodium chloride and molten sodium chloride. So you've got it when it's solid in this test, and you've got it when it is molten, which just means melted, in the test on the right. You've got the observations in table 1. So solid sodium chloride, the bulb does not light up, and therefore they're saying it does not conduct electricity. Under molten sodium chloride, they can see the bulb does light up, and therefore they're saying it does conduct electricity. So that's, to me, sounds like they've got their table correct. So what we need to do is draw one line from each statement to the correct reason. Solid sodium chloride does not conduct electricity. Why is that? The ions are fixed, they are mobile, they are neutral, or they are vibrating. Well, you should know that if you've got a solid, the particles cannot move. So therefore, they are fixed in position. They can't move, and therefore they cannot carry the electricity. Whereas molten sodium chloride, it's been melted, and therefore they are able to move. Because they are able to move, we say that they are then mobile. Mobile means in order to move. So that is question 1, and you could give yourself a mark out of 10 for that. Okay, so we're now going to look at question 2 of this chemistry paper. Question number 2, this question is about the halogens. Which group in the periodic table is known as the halogens? Well, we should know that group 1 is called the alkali metals. Group 2 is the alkali earth metals. Group 0 is called the noble gases. Therefore, group 7 is our halogens. So, a fluorine atom has 7 electrons in the outer shell. Figure 8 shows part of a dot and cross diagram to represent the molecule of fluorine, F2. Complete the dot and cross diagram. You should only draw the electrons in the outer shells. So we can see we've got a covalent bond here because they're sharing electrons. One atom, we're doing it with dots. One atom, we're doing it with crosses. They are both in group 7 and they want to get 8 electrons into their outer shell. So what they are going to do is share 1 electron with each other. So in the middle, 1 cross from the atom that has the cross electrons and 1 electron from the atom that has the dot electrons go into the middle. Now, we know that each fluorine has 7 electrons. So what we now need to do is make sure that each atom has the correct amount of electrons around the extra shell. So we can we know we've got 1, 2, 3, 4, 5, 6, 7 electrons for the dots 1, and now we can do 1, 2, 3, 4, 5, 6, 7 electrons for the one that has crosses. So we can see that each fluorine now has 8 electrons, which shows how it's covalently bonded. You would get 1 mark if you put that part in the middle, and you get the second mark for making sure that each atom has the correct amount of electrons on the outer shell. You don't need to worry about putting them in pairs to get the marks. So question 2.3, chlorine reacts with potassium bromide solution. Complete the word equation. So you've got chlorine reacting with potassium bromide. Now, when you get a question like this, is effectively a simple displacement reaction. So you've got to work out logically what might happen with these different chemicals. Well, chlorine is higher up on group 7 than it is than bromine is. So it comes along and it effectively kicks the bromine out. So it would make potassium chloride. We change the chlorine to a chloride to show it's now a compound. And then what is left over, bromine, is left by itself. So it makes bromine and potassium chloride. I can tell where I've got to put each product because of the lines that they've given us in the question. Question 2.4, what type of reaction happens when chlorine gas reacts with potassium bromide? Well, I said this in the previous question. What we've got is chlorine kicking out the bromine, so it is a displacement reaction. A decomposition reaction means when a substance is getting broken down. We're not getting that here, we've just got things swapping about. Neutralization is to do with acids and alkalis. And precipitation is when you make a solid from 2 solutions. And we haven't got that happening in this equation. So, even if I didn't say it on the question before, you could have worked out by process of elimination, it is a displacement reaction. Question 2.5 then, complete the sentence. Chlorine is more reactive than bromine. This is because chlorine gains blank more easily. So it's either an atom, an electron, a neutron, or a proton. Now we should know in chemical reactions, it's always the electrons that are getting either shared or being given or being taken. So it's because our chlorine is able to gain an electron more easily. Question 2.6, how does the size of a chlorine atom compare to that of a bromine atom? Complete the sentence. A chlorine atom is blank a bromine atom. So it's either bigger than, the same size, or smaller. Now, a chlorine, if you look at your periodic table, okay, chlorine is higher than bromine on the periodic table. So therefore, because it is higher up, and we can see with the numbers that it's got as well, in terms of protons and electrons and neutrons, it is smaller. So we can say chlorine is a smaller than a bromine atom. Okay, so moving on to question 2.7, we need to give a reason for our answer for 2.6. So why have we said that chlorine is smaller? Well, we can see from the periodic table that it has fewer electrons than bromine. Therefore, it would have fewer shells of electrons. Okay, it's only a 1 mark answer, so it's just saying that because it has a smaller amount of electrons, it is a smaller atom. Question 2.8, fluorine reacts with chlorine to form ClF3. Balance the equation for the reaction. So we've got chlorine plus a certain number of fluorines makes 2 lots of ClF3. So what we need to do is work out the amount of atoms we've got on our left side of the equation and our right side of the equation. So on our left side, we've got 2 chlorines and we've got 2 fluorines. On our right side, we've got 2 chlorines because of the big 2 in front, so 2Cl, but then we've got 2 lots of F3. So we've got 2 lots of 3, which gives us 6 fluorines. Now, in order to get 6 fluorines on this side of the equation, we would need to times our F2 by 3. That means we would then have 6 fluorines that side, and therefore the amount of atoms each side of the equation is the same, and it's balanced. Question 2.9. Explain why fluorine is a gas at room temperature, and we need to use the words energy, forces, molecules, and weak. So, we know that fluorine is a gas at room temperature, so we can imagine it as F2 floating about in the air. Now, there would be forces between them, but because they are a gas at room temperature, we can think about how strong those forces are going to be. And we can look at the words we've been given, identify we've got weak and forces. So the question is pretty much telling us fluorine has weak forces. And these forces are between the different molecules of fluorine. So fluorine has weak molecules between the different fluorine molecules. Now, because they have weak forces, we then need to think about how we can link energy into it. And because they are incredibly weak, you don't need much energy to come along and break and overcome these forces of attraction. So your final mark would be little energy is needed to overcome these forces of attraction. Now, whilst it's not needed in this question, the scientific name of these forces are called intermolecular forces. So, simple covalent compounds have weak intermolecular forces, therefore they have low melting and boiling points, which is why they are normally gases at room temperature. Okay, so we'll now move on and have a look at question 3. This question is about acids and bases. Question 3.1, which ion is found in all acids? Well, that is H+. H+ is the acidic ion. Okay, and the other one you've got to know, which is OH-, which is the alkali or base ion. And we can demonstrate this because of the neutralization equation, which is H+ plus OH- makes H2O. So you've got acid plus alkali makes water, okay, which is neutralization. So you just need to make sure you remember these two key ions. But for acids, it is H+. So question 3.2, zinc nitrate can be produced by reacting an acid and a metal oxide. Name the acid and the metal oxide to produce zinc nitrate. Now, because it is a nitrate, the type of acid we would have to use is therefore nitric acid. You should remember that sulfates come from sulfuric acid. Nitric acid makes nitrates, and hydrochloric acid makes chlorides. Now, the metal oxide that we would have to use is effectively, you just substitute the name of the metal that you're using. So we could use zinc oxide plus nitric acid makes zinc nitrate. In the equation, zinc nitrate is written as this, okay? What does AQ mean? So AQ is one of the state symbols. That means it is aqueous, which means dissolved in water. The four that you need to know, okay, is S, which is obviously solid, liquid, which means a pure liquid, normally dissolved, pure water. And then you've got gas, which is G. And then you've got aqueous, AQ, which means it is a solution. You've got a solid dissolved into a liquid. Question 3.4, the pH of a solution is 8. Some hydrochloric acid is added to the solution. Suggest the pH of the solution after mixing. So we should know that the pH scale goes from 0 to 14. pH is 0 to 6 is an acid, pH 7 is neutral, and pH 8 to 14 is an alkali. Now, if you've got it already as an alkali and you're adding acid to it, then you are going to be moving down the pH scale. Because it's only saying suggest, it's not saying work out, you just need to put a logical answer and demonstrate you know which way it is going. So any number between 0 and 6 or 0 and 7 would actually then get you the mark in this question. Okay, so the last part of this question, 3.5, says table 2 shows the solubility of 3 solids in water at room temperature. You've got phosphorus oxide, and the amount of solid that dissolves in 100 centimetre cubed of water is 50. You've got silicon dioxide, and that doesn't dissolve at all. And you've got sodium hydroxide, which dissolves the most. A teacher labelled these 3 solids A, B and C. She gave the student an information shown in table 3. So you can see she's got the 3 solids A, B and C, and you've got the observation when added to water. So it either makes a solution or it doesn't dissolve. You've then got the pH of the solid in the water. So she's used a substance to test for pH. And we can know that pH 14 is an alkali, pH 2 is an acid, and pH 7 is neutral. Describe a method that could be used to identify each of the 3 solids A, B and C. You must use an indicator in the method. use tables 2 and 3 to help you get your answer. Now, it's told us we need to use an indicator. So therefore, my first part of thinking for this question would be to go with the obvious indicator that I know. And the obvious one is universal indicator. So I need to identify and figure out a plan how to identify which of these substances is A, B, and C. So if I look at the information about solubility, I can see that silicon dioxide does not dissolve at all. And then I can see what happens when it's added to water. I've got one of them that does not dissolve at all. So therefore, C is going to be silicon dioxide. And we can tell this because it is not soluble and it has not dissolved in water. So we know what C is, so now we just need to figure out which one is A and which one is B. Now solubility isn't going to help us here because they both dissolve and they've both made a solution. So we can't tell from that. So what we are going to have to do, okay, is use the pH. What we can do then to figure that out is add, so to figure out A and B, we can use universal indicator. Okay, now sodium hydroxide, we should notice this word hydroxide, that is an alkali. Okay, it's normally the standard one we use in the lab to neutralize hydrochloric acid. Because it's an alkali, we then know from our pH scale that it is therefore A. So we use, to figure out A and B, we can use universal indicator. A is an alkali, which is a hydroxide. Therefore, B must be phosphorus oxide. Okay, and that is how you would go about tackling 3.5. Okay, so we'll now have a look at question 4 in this paper. This question is about the elements of group 2 of the periodic table. Figure 9 shows the positions of 4 elements, A, B, C and D in the periodic table. What element is in group 2? So you can use the periodic table you'll have in the exam for this, and you can see that obviously your group 1 is there, group 2 is there, then you have the transition metal blocks, and then you have 3, 4, 5, 6, 7, and group 0 at the end. So which one is in group 2? It will be B. Group 2 metal carbonates break down when they are heated to produce a metal oxide and a gas. So it's told you metal carbonate makes a metal oxide and a gas. Name the 2 products when calcium carbonate is heated. So what I would do is try and work out what the equation would actually be. CaCO3, and it's being broken down into 2 things. Now, as it is a carbonate, okay, what gas is likely to be produced? Well, it's likely to be CO2. So I've used up a carbon atom and 2 oxygen atoms from this compound. So what does that leave me with? Well, it leaves me with 1 calcium atom and 1 oxygen left over. So therefore, my products would be calcium oxide and carbon dioxide. What type of reaction happens when a compound breaks down? Burning, decomposition, neutralization, or reduction. If you are breaking something down, you are decomposing, or it's a decomposition reaction, sometimes called a thermal decomposition reaction, which means you're breaking down using heat. Question 4.4. The metal carbonate takes in energy from the surroundings to break down. What type of chemical reaction does this? Well, combustion, this is a fancy word for burning, so that doesn't take in energy, so it's not that. Electrolysis generally produces a bit of heat, so it's not that. And it's between endo or exothermic. You should remember that exothermic gives heat out to the surroundings, or releases heat to the surroundings, therefore you get an increase in temperature. You can think of it as heat being exited from the chemicals, so therefore heat being taken in or absorbed is an endothermic reaction. Question 4.5. Figure 10 shows the volume of gas produced when a group 2 metal carbonate is heated. You've got a graph here, you've got the mass of group 2 carbonate at the bottom, and you've got the volume of gas being made at the side. A student collected 5.2 decimeter cubed of gas. What mass of group 2 metal carbonate is heated, and is only 1 mark. So you are obviously going to use the graph to help you do this. Don't overthink it. You would go to 5.2. Reading the scale properly, you've got a gap of 2 decimeter cubed, and you've got 5 squares, so therefore each square is going to be worth 0.4 decimeter cubed. Go up, so it goes 4.0, 4.4, 4.8, 5.2. So this line here is representing 5.2. You go along, and then you can go down, so that gives you 32 grams. So we know that 32 grams is equal to 5.2 decimeter cubed of gas. Question 4.6. Calculate the mass of the group 2 carbonate to produce 24 decimeter cubed of gas. Use your answer for question 4.5 to help you. Now, there's actually 2 different ways of doing this. I think I actually prefer the second way of doing it, but I'll go through the first way. If you know that 32 grams makes 5.2, what you can do is 32 divided by 5.2, and then you want 24, so you could times it by 24, and that would give you your answer of 148 grams. Now, the other way is actually just to try and use the graph again to help you do it. If you know, well, if you look at the graph and you know that you're after 24 decimeter cubed of gas, but your y-axis only goes up to 16, okay? So what you might want to do is look for a number on your scale that could go into 24. So, for example, we know that 12 is half of 24. So if we know how much carbonate is needed to make 12, we can just double it, because it's a straight line, and then work out how much it would make to 24. So you can go along at 12, and then down, again, using the same process as before. So to make 12 decimeter cubed of gas, you've got 74 grams. So therefore, to double it, to make 24 decimeter cubed, you would need twice the amount of grams, which is 148 grams again. So your answer is 148. Doesn't matter how you get to 148, but that gets you the 2 marks. Okay, so the last part of this question is question 4.7. A student heated different masses of a group 2 metal carbonate. They measured the volume of gas produced. Figure 11 shows the graph of their results. They calculated the gradient of the line in figure 11, but they've made 2 mistakes. You've got their calculations and what they did here, and the correct formula for the gradient is the increase in the volume of gas divided by the increase in mass of the group 2 metal carbonate. What they've done is 4 divided by 750 equals 0.00533 centimetre cubed per gram. Identify the 2 mistakes that they've made and then calculate the gradient of the line. So if we look at this graph really carefully and go through their process of doing it, increase in the volume of gas. If we look at the axes, we can see it's gone from 250 up to 1000. So the difference is 1000 minus 250 is 750 centimetre cubed. So I think they've done that part spot on. They then need to calculate the increase in the mass of group 2 that is heated. So what they've done is go from 1 to 4, but if we have a look at their calculation, to calculate the difference, they've done 5 minus 1 equals 4. Well, they haven't gone up to 5, they've only gone up to 4, so it should be 4 minus 1 equals 3. So their first mistake is they miscalculated the increase in the mass of the group 2 metal carbonate. Mistake number 2 then, if we have a look at what they've done, so we've got our 2 numbers now, 750 and 3. They did 4 divided by 750. Well, what they've done then is divide the increase in mass over the volume of gas, which is the wrong way round. They should have done it this way round, volume divided by the increase in mass. So their second mistake is they divided the numbers the wrong way. So you would get 1 mark for identifying each of the mistakes, and then you would get 2 marks for then actually working out the proper gradient. So we know it should then be 750 divided by 3 equals 250 centimetres per gram. So question 4.8 then. A student repeated the experiment with a different group 2 metal carbonate, XCO3. The relative formula mass of XCO3 is 84. You've got carbon, which has the mass of 12, and oxygen has a mass of 16. Calculate the relative formula mass of the element X. You've then got to name metal X, and obviously we'll need to use our periodic table. So if we know that XCO3 is equal to 84, what we could do is work out how much CO3 is, and the difference would then be the element that is X. So carbon we know is 12, so we've got 1 lot of 12, 1 times 12 is 12. We've then got 3 lots of oxygen, 3 lots of 16 is 48. If you add those together, that gives you a total of 60. So 60 out of the 84 is CO3. The difference then, so 84 minus 60 is going to equal 24, and that is the mass of element X. So the mass of element X is 24. We can then look at our periodic table to figure out what element it is, and it is magnesium. So that was a big question, question 4, 16 marks for it. Okay, so moving on to question 5 then. This question is about electrolysis. A student investigates the mass of copper produced during electrolysis of copper chloride solution. Figure 12 shows the apparatus. So you've got your power supply, you've got your electrodes, and we're using copper chloride solution. So what gas is produced at the positive electrode? Now, if we look carefully at what chemical we're using, it is copper chloride. So copper is going to form positive ions, and chloride is going to form negative ions. Now, the negative ions are going to be attracted to the positive electrode, So the chloride ions that are in the solution are going to be attracted to the positive electrode, and therefore you would get chlorine gas being made there. Okay, and you can see at the negative electrode, we're getting the copper being deposited because the copper moves to the positive electrode. So remember, opposite charges attract, the oppositely charged ions will go to the different electrodes. Question 5.2, as we've just seen, copper is produced at the negative electrode. What does this tell you about the reactivity of copper? Now, the rule is that if a metal is more reactive than hydrogen, then hydrogen will get formed, not the metal. But if the metal is less reactive than hydrogen, in reverse, then that metal gets formed instead of hydrogen. So that is just a key rule. Comes up more actually on the higher tier paper than the foundation, but this is just a key rule you just need to know. So what does it tell you about copper? Well, it tells you it's the first one here. Copper is less reactive than hydrogen, and that's why it forms at the electrode. If you were doing it as a solution of lead chloride, now lead would be more reactive than hydrogen, and therefore lead would not form at the cathode, it would be hydrogen instead. Question 5.3 then. You've been given this table of the students' results. You've got the time in minutes, 1, 2, 4 and 5. You've got the total mass of copper being produced in milligrams, and you've got the experiments and their means. Determine the mean mass of copper produced after 3 minutes. So go to your mean column. After 1 minute, it's 0.6, 2 minutes is 1.2, and 4 minutes, it jumps to 2.4. So we can have a look at what the pattern is that is happening. Now, it's only a 1 mark question, so don't overcomplicate it, okay? What pattern is happening as it goes up? So effectively, what's happening is doubling each time, or it's going up, sorry, by 0.6 each time. So 0.6 to 1.2, then you would add another 0.6 to give you 1.8. So your answer after 3 minutes would be 1.8 because it's going up 0.6 each time. Then question 5.4, calculate the mass of copper, mass X of copper produced in experiment 2 after 5 minutes. So if I go back to this table very quickly, I can see that for 5 minutes, they've given me my mean value, which is 3.06, and they've told me 2 of the experiments were 3.02 and 3.01, but I've got to figure out the mass of this second experiment, X. So what I've done, just at the top here, I've just rewrote these key numbers so I don't have to flick back between the screens. So if I know experiment 1 was 3.02, I know that experiment 2 is what I'm figuring out is X, experiment 3 is 3.01, and my mean, if I calculate it, is 3.06. So what can I do in order to find out X then? Well, if you think about how you would calculate the mean to begin with, you would add them all together and then divide by 3, because that is how you do it, assuming that there's no anomalies. Now, what we could do is rearrange this equation, or we can do it a slightly simple way. We can see the difference between our 2 values that we've got, okay, and our mean, and see what the differences are, and therefore we can add it onto X. So 3.02 is 0.04 less than our mean. So negative 0.04. below our mean. Our third experiment is 0.05 below our mean. So both of these values that we've got give us a total of being 0.09 below our mean. So therefore, if we were then going to calculate our mean, experiment 2 must be therefore 0.09 higher than the mean. So 3.06 plus 0.09 makes 3.15. Okay, so we're predicting that 3.15 is X. Now what we can do is check it, get our calculator out. We could do 3.02 plus 3.15 plus 3.01 divided by 3, and that does work out to be 3.06. Okay, you could also just do a bit of trial and error if you don't know how to rearrange the equation until you get the answer that actually is there. But the final answer for 2 marks is 3.06. Question 5.5 then. The copper chloride solution used in an investigation contained 300 grams per decimetre cubed of copper chloride solution in 1 decimetre cubed of water. The students used 50 centimetre cubed of copper chloride solution in each experiment. Calculate the mass of solid copper chloride used in each experiment. So the equation that you would need is what is linking together concentration, mass and volume. So hopefully you know concentration equals mass over volume. You can rearrange it, so mass is equal to concentration times by volume. So we are figuring out the mass. We have been told in the question that our concentration is 300 grams per decimetre. That is a fact, that's what we've been told. And we've also been told that the volume of copper chloride solution is 50 centimetre cubed. But this is in centimetre cubed, our concentration is in decimetre cubed, which is a much, much bigger amount. So we would have to convert centimetre cubed to decimetre cubed before we could plug it in our equation. Now, to convert centimetres to decimetres, because decimetres is a much, much bigger unit, you divide by 1,000. So if you did 50 divided by 1,000, that equals 0.05. So our volume that we would use is 0.05 decimeters cubed. Times that by our concentration, which is 300, equals 15 grams. So you'd get 1 mark for figuring out the correct equation and substituting it in, and then 1 mark for getting to your final answer. Okay, so moving on to question 6 then. This question is about sodium and chlorine. Figure 13 shows the positions of sodium and chlorine in the periodic table. So you've got sodium in group 1, chlorine in group 7. State one difference and one similarity in the electronic structure of sodium and chlorine. So if we go for a difference first then, well, we can see they're in different groups, 1 and 7. And it's our group number that determines how many electrons there are in the outer shell. So a difference would be sodium has 1 outer electron, chlorine has 7 outer electrons. A similarity though, well, we can see although they're in different groups that are going down, okay, they're actually in the same period. Now the periods show how many shells there actually are. So they're both in the third period, so they would both have 3 shells of electrons. The only difference being is how many electrons there are in the outer shell. So question 6.2, sodium atoms react with chlorine atoms to produce sodium chloride compound. Describe what happens when a sodium atom reacts with a chlorine atom. Write about electron transfer in your answer. So if we draw out a quick sketch of what's happening then in terms of the outer shells, we've got sodium that has 1 electron, we've got chlorine that has 7. So how are they going to help each other out? They want a full outer shell, so sodium is going to give its 1 electron to chlorine. So you could summarise it as this. Sodium gives 1 electron to chlorine. Now in that one sentence there, you've actually got 2 marks because you've said what is happening and you're saying how many electrons are moving. So 1 mark for saying that it's sodium giving it to chlorine, 1 mark for saying it's 1 electron. What is going to be created as a result of that? Well, the first thing is, because sodium loses an outer electron, it then becomes a positive ion. Okay, so sodium becomes a positive ion because it's lost an electron. Chlorine becomes a negative ion. Question 6.3, the reaction between a sodium and a chlorine is an exothermic reaction. Complete the reaction profile for the reaction between sodium and chlorine. So the reaction profile is what it looks like in terms of energy. So you've got your reactants, and we know an exothermic reaction gives out energy. So at the end, it will have less. So at the bottom, your products would have gone down in the amount of energy they've got. Now, in order to make the reaction happen though, we sometimes have to put a bit of energy into it. We call that the activation energy. Okay, you don't need to add these labels for the marks, but the shape looks like this. So you've got the activation energy bump. That's the energy you put in to actually make the reaction happen, and then the products end up with less energy at the end. Question 7 then, the last question in this paper. A student plans a method to prepare pure dry crystals of copper sulfate. So hopefully you've done this required practical, which is making those blue crystals of copper sulfate. This is their method. Add 1 spatula of calcium carbonate to dilute hydrochloric acid in a beaker. When the fizzing stops, heat the solution with a Bunsen burner until all the liquid is gone. This method contains several errors and does not produce copper sulfate crystals. Explain the improvements that the student should make so that pure crystals of copper sulfate are produced. So, what I would do is then break it down into the mistakes and then the improvements to the method. So the key thing that we've got to do is actually say how it could make copper sulfate crystals. Because what if they reacted together? Calcium carbonate and hydrochloric acid. That would not make copper sulfate. There's no copper and there's no acid that would make a sulfate. So, mistakes, what you could say is that they should use maybe copper oxide and sulfuric acid to make copper sulfate. Okay, so the key mistake is they used the wrong chemicals. What should they do to improve it? Well, they should use the right chemicals, copper oxide and sulfuric acid. The other key things that their method is that they've missed several key steps out of it. They've said they should add 1 spatula of calcium or their chemical. Now, when you do this practical, hopefully you remember, you add the copper oxide to excess. So you add copper oxide till excess, which means you keep on adding it until the reaction stops. And that shows that all of the acid then has been neutralised. So this shows that all acid has been neutralised. Now, when you've got all of that powder in your solution, you've got to take it out before you can then start heating it. They've added the powder and then they've started heating straight away. You need to get rid of that excess powder, and they can do that by filtering. So you can remove the excess powder by filtration, which will make sure that when you're heating it, there's no extra powder in there. Now, again, heat, and they've heated it until all the liquid is gone. If you heat it until all the liquid is gone, then your crystals will start to break down. What you need to do is heat it until there's a little bit of water left, and then you leave it to just let it cool slowly to allow the crystals to form. So you heat until there is a little water left, this allows crystals to form. Okay, so what we've done here, the last point as well, is that at the end of a practical, you normally, when you've got your crystals, is you dry them on filter paper. So, if you haven't done this practical, under question 7 in the description, there'll be a video, an excellent video that goes through how to perform this practical perfectly. So make sure you watch that. But what we've done here is clearly identified the mistakes that they've done and what actually they should do in order to get their pure dry crystals of copper sulfate. Right, hopefully that all made sense. And as I said, this exam paper and the actual mark scheme for it are attached below. Thank you very much.